start with a bit of a welcome and introduction to the group I've got here today. So my name is Alison Potter. I'm a principal at Grimshaw, one of the now growing number of practices with commitments to designing net zero carbon ready buildings, measuring carbon impacts throughout each stage of the design. Really like to welcome you all here today. I'm joined by Philip Oldfield, Associate Professor in Architecture at UNSW, who's been conducting extensive research and in understanding embodied carbon, and Ross Donaldson, a member of the Climate Action and Sustainability Task Force and author of 7 CPD modules for the AIA on this very topic. I would like to start by first acknowledging on behalf of the Australian Institute of Architects and to pay my respects to the Aboriginal and Torres Strait Islander people across Australia as the traditional custodians of our lands, water and seas. We recognise their unique ability to care for country and their deep spiritual connection with country. We honour elders past, present and emerging, whose knowledge and wisdom will ensure the continuation of Aboriginal and Torres Strait Islander cultures and the values which uphold them. And I wish to personally acknowledge the Wurundjeri people as the traditional custodians of the land in which I sit today. So we're here today to discuss how, as architects, we can ensure that we can be active participants in designing and delivering buildings which work our way towards net zero carbon, and to understand what actions we can take to reduce carbon in our designs. So I'm going to pass over first to Philip. He's going to give us a presentation on embodied carbon. And then I'll hand over to Ross afterwards, who'll present some key extracts from his lecture series with some practical applications around how we can actually embed this through our design. So after that, I look forward to facilitating a great discussion with following these 2 presentations. Please don't be shy putting forward your questions into the chat at any time during the presentation, and I'll endeavour to bring as many of them to the group as possible during 20 minutes. So I'll just pass over to Phil.
Fantastic.
Thank
you, Alison. Good morning, good afternoon, everybody. Let me try and share my screen. Current slide. There we go. Hopefully you can all see this. Real pleasure to talk to you today a little bit about embodied carbon. I've been asked to write the Acumen note on embodied carbon, so some of the lecture here touches on some of those kind of things that are within the kind of note. But first, I want to start at a very broad stage. I think if you're in the room today, you will agree with me when I say to build, the verb, is a societal good. There's not much more we can do for society that has an intrinsic value than to build houses, to build hospitals. The United Nations say that 1.7 billion people globally currently have inadequate housing. That's a lot of houses we need to build, a lot of houses we need to retrofit, a lot of houses we need to, a lot of schools, a lot of great places that we can build, and we can improve people's lives through building. So from a societal perspective, building is good, but also quite controversially, to build is inherently environmentally bad. There are very, very few buildings around the world that have a positive environmental impact, that are regenerative. The vast majority of our buildings have a carbon footprint. And what we know is that the graph on the right-hand side shows 37% of all anthropogenic CO2 emissions are from buildings. It's either constructing the buildings, building them, or operating them. Now, if you compare that to the much maligned aviation industry, which is 3%. So we know our profession is partially, at least, responsible for a huge amount of society's carbon emissions. So just to kind of sum that up, we know we need to build, but we also need to radically change the way we build to reduce carbon emissions. Now, we also need to radically rethink or to recalibrate how we build, given where carbon emissions come from. So this is a diagram that shows where carbon emissions come from across a building's life. And, you may extract iron ore to fabricate a steel beam. So there's the extraction process on the left-hand side, you have transportation to the factory, there's a manufacture, using an electric arc furnace, which is usually powered by coal, and then there's transportation to the building site, and you lift the the steel beam into a building, and then you operate the building across its life, and then we demolish the building in 50 years' time, and then we might recycle the building. At every stage in this diagram, there are carbon emissions. At every stage in this diagram, there are environmental impacts. Part of the challenges are building regulations. Much of our knowledge, much of our education, which I'm partially responsible for as an academic, is focused on this. It's focused on one of these stages. And really, we've spent the past 5 years or so trying to open up this diagram to really understand and interrogate carbon emissions across buildings' life cycles. So out of that, we have 2 main categories, which I'm sure you're all familiar with. We have embodied carbon, and our embodied carbon is the greenhouse gas emissions emitted from extracting raw materials, processing those materials, assembling components, effectively building the building in the first place, refurbishing the building over its life, and then there's the end of life emissions. Then you can break that up into upfront embodied carbon, which is getting the building built, recurring embodied carbon, which is the maintenance and adaptive reuse of the building across its life, and then end of life kind of emissions. And when I say embodied carbon, what I really mean is embodied greenhouse gas emissions. So it covers all the greenhouse gas emissions, methane, CFCs and other things, but just normalized back to carbon. And then we've got operational carbon. So we can kind of simplify that diagram down to these 2 elements. And historically, we go back 10 years, maybe 15 years, the kind of knowledge was that operating emissions were responsible for about 80% of this, and embodied were responsible for about 10 to 20%. And that's why, understandably, much of our focus has been on energy efficiency. It's been on reducing the environmental impact of how our buildings operate. Our current knowledge, current thinking says this has changed. Our current knowledge is probably closer to 50-50. Now, why has that changed? Well, one, we've got better at measuring embodied carbon, although still some challenges, which I'm sure you're all aware about and which Ross is going to touch on, I think, later. But also, we've started to decarbonize our electricity supply. We've got better at insulating buildings. We've got better at double glazing. We've got better at making our buildings more efficient. And that means, relatively speaking, embodied carbon has increased its importance. The slightly confronting thing is, if we fast forward another 7 years, by 2030, if we say all new buildings are going to be net zero operational, 100% of emissions will be embodied carbon. So across 15 years, our discipline has shifted its focus from the operating side of things, from energy efficiency, and to a point where the materials will be 90 to 100% of carbon emissions across a building's life cycle. And so that gives us the responsibility to really focus in on this and to ensure that we can measure it and we can kind of reduce it. I've simplified things a little bit there. In reality, actually, I think we need to acknowledge as well that carbon emissions across a building's life cycle are dynamic. They change. They really do change. This is a diagram that kind of explains over 50 years. You build a new building today, this is what its carbon emissions will look like. And even this is simplified a little bit. So you've got upfront embodied carbon emission in year 0, and then you've got operating emissions. And operating emissions are different. They don't all happen in year 0. They're cumulative. They build up over time. Then after 10 years, you might, replace the finishes and fittings. So you've got a little bit of recurring embodied carbon, and then you've got more operating. But you can see the angle of those operating emissions changes. The reason that changes is the carbon impact of our electricity grid is decarbonizing. We are shifting at a kind of state and federal level towards renewables. At the moment in New South Wales, for example, for every kilowatt hour we use, it's about 0.79 kilograms of CO2. But that might reduce to 0.5, 0.4, 0.3. And by the time we get to about 2050, that will hopefully be about 0.05, pretty close to 0. So those operating emissions, their importance, their relative importance will change over time. The outcome of all of this is, look, all our measurements we've been doing now, any new building we build, we're expecting about 50 to 70% of its total life cycle emissions to be embodied moving forward. That's assuming we decarbonize our grid. on a basis like this. So embodied carbon is significant. It's important. Out of that, we see lots of different organizations come out with embodied carbon reduction targets. I won't go through them all, but you've got GBCA, REBA, LETI, and effectively most of them fall into two categories. One, by 2030, a reduction of 40 to 65% emissions, and then this aim for net zero whole of life or net zero embodied carbon by 2050. I will point out the Global ABC Roadmap in Africa has a delayed embodied carbon target, and that's fundamentally because there's a need for materials, a need for carbon emissions to lift billions of people out of poverty. That's going to require concrete, that's going to require materials. So there is a bit of a delay, and that in the global north, that we have a responsibility to accelerate our reductions to allow poverty to be alleviated in other places as well. So how do we do it? And I'm going to spend, I think, about 6 or 7 minutes just rattling through some options. But the key message here is it's the conversations at the beginning of a design phase that have the biggest impact. The diagram here on the left-hand side is about 10 years old now, but it's incredibly powerful. And it shows what the embodied carbon savings are for different strategies. And in the planning stage, if we build nothing, we can save 100% of embodied carbon. Now, that's not always possible, obviously. We don't always want to build nothing. As I said at the beginning, we have a societal, moral, ethical responsibility to build. But if we build less, if we adaptively reuse, we can maybe save 80%. If we build efficiency, we can maybe save 40, 50%. But if we save embodied carbon to the end, we're limited. We're limited. If we just change some materials, concrete to low carbon concrete, we might save 5 to 10%. So the decisions we have in the initial stage of design are fundamental to reducing embodied carbon. And I can talk a little bit about this. I won't talk about build nothing because it's not really an option a lot of the time. But when we talk about build less, we're talking about adaptive reuse. We're talking about building smaller. I mean, some of the most important things we can do is to build smaller. Now, that's incredibly political. You know, we have some of the largest houses in the world, as this diagram shows. If we can build smaller houses that have the same function, that have the same performance, that have the same, you know, impact on family, on people who live there, then we can save significant amounts of embodied carbon. So if we say every square meter, typically every square meter of a residential building is about 660 kilograms of CO2. If we can reduce 1 square meter, we can save 660. For a commercial building, it might be 1,000. So if we can save 1 square meter in a commercial building, we can save a ton of carbon like that instantly. And it's not like adding insulation where that saving builds up over time. It's an instantaneous saving. We can also adaptively reuse our existing building stock as well. And look, obviously here in Sydney, we've got QQT, which I think is one of the most radical adaptive reuses, certainly of a skyscraper that I'm aware of, where a building that was coming towards the end of its life has been rejuvenated and extended, saving around 8,000 to 10,000 tons of CO2. But it's not just a retrospective policy, it's also a prospective way of thinking as well. We need to be building in a way that arguably we can think about future uses of our buildings as it is. Certainly in Sydney, we've seen, you know, cultural buildings such as the Sydney Stadium, for example, pulled down in 25 years. You know, if we can get buildings to last longer, or if we can design them in a way where they can be disassembled, deconstructed, where their materials can be easily reused rather than wasted, that will also help us in the future reduce embodied carbon. So there's quite radical ideas such as buildings as material banks. Conceptually, instead of thinking about a building as a resting place of a material, we think about a building as a temporary, long-term resting place of a building material. And obviously there's large-scale commercial, social, and political challenges to this. It doesn't just fall on us. We can also build clever as well, but this only has probably a 50% potential. These strategies do. I was amazed when I visited Smart Design Studio here in Sydney. If you look at the structure, it's an adaptive reuse of a 150-year-old building. But look how thin that steel is. That steel has been engineered to within literally an inch of its life. The reason for that is you go back 150 years, labor's cheap, materials are expensive. So you can afford to have a lot of people on site, really, you know, but you can't afford to have too much material. Now the cheapest thing to do is to put a 200 mil concrete slab across everything. So this idea that materials are precious and how we can, you know, how we can dematerialize everything to within an inch of its life, ensuring safety, ensuring regulatory compliance as well. And we're starting to see developments such as this, which I think is amazing, called the mini-mass hybrid beam, where instead of looking at a conventional beam, they have optimized structurally what materials need to be in that beam and what materials don't. And it kind of goes back to the work of, you know, even Fry Otto, you know, Nervi and others who did things like this, who really looked at, and we've got the technology now, we've got AI and all these kind of things to really dematerialize what we do. But it's not just a technical engineering question. This is a fundamental design question. And here's a building that I like to talk about. This is Renzo Piano's Intesa San Paolo Tower in Turin. I talk about tall buildings a lot. It's my problem. I'm sorry. So this is a tall building. Like a lot of tall buildings, wants to have an open plaza underneath the building, right? So they have designed a truss to transfer out all the structure, and that truss is bright red. That truss to transfer out the structure and open up the ground is 2,350 tons of steel. That truss will have an embodied carbon of 6,815 tons of carbon dioxide equivalent. My question is it worth it? Is it worth it? Is the social public benefit of having the open ground with no columns coming down, is it worth 7,000 tons of CO2? There's no calculator that's going to give you that answer. There's no tool that's going to tell you that. You know, that's about interpretation and conversation and other things. If it was me, I'd let the columns come down to ground and let people walk around the columns. But look, if you did that, you could potentially save several thousand tons of CO2. So every design decision we make needs to be interrogated within the context of embodied carbon. I'm running out of time, so I'm only going to talk about one or two more things. I do want to talk about types of material and material exchange. If you're anything like me, you were probably taught something like this at school. This is the food pyramid, and you've got foods you should be eating at the bottom. You eat everything off the pyramid. You know, we all eat some lollies at the top, but we all meant to have lots of vegetables at the bottom. You're meant to have more at the bottom than you are at the top. And I think a similar approach is needed in our material scape. And the Danish Institute of Architects, I forget, maybe the Danish Institute of Architects, Denmark, someone in Denmark has produced a material version of this. And again, it's this idea that we should be using more materials from the bottom than the top. You know, I'm not someone who says we shouldn't be using concrete. I think we should use as little concrete as we can, but there's not a lot of what we can build without it. There's not a lot of we can build without it, but we can really start to question when we use concrete as well. And where possible, use materials that are low carbon. But again, a reminder, this can only save 30, 40, 50% of embodied carbon. So some of the research we've done really, for example, looks at, we took an 18-story building in Sydney and we ran it through a number of different structural systems. So it had a base embodied carbon of about 750 kilograms of CO2. We changed it to a flat slab and saved 6%. We changed it to a post-tension slab and saved 8%. We changed it to a steel deck and didn't save anything much. But if you look at towards the end with a whole timber structure, that still has 5 stories of underground car parking, which we could have got rid of and saved a lot more. But that saved about 18 to 32% of embodied carbon just by switching to a timber kind of structure. And timber and biomaterials are obviously a great opportunity. But if you had also done dematerialization on this building, if we'd also really tightened the net to floor, I think we could have saved a lot more. So to kind of sum up, you know, the question is, what can we do today? And I hear a lot of time, you know, well, we've got to wait till there's regulation. We've got to wait until there's a consistent way of measuring. I disagree. You know, there's this great report just come out by the WBCSD and Arup called Net Zero Buildings Halving Construction Emissions Today. And this report says we can reduce embodied carbon 50% today using conventional approaches. But the key is there's no silver bullet. It's not just about replacing concrete and timber. It's not just about making the building more efficient. It's about fundamentally across skin, space planning, finishes, structure, services, across all the different layers of a building, really considering embodied carbon. And if we do that today, we can save 50% of embodied carbon right now. So some of the conclusions in the Acumen note are, firstly, one, for many new buildings built today, embodied carbon will be the largest contributor to total greenhouse gas emissions across its life cycle. Not necessarily all buildings, but a lot of buildings, that will be the case. Two, there's very strong evidence that we can significantly reduce embodied carbon by up to 50% right now, not waiting for some exotic concrete mix, not waiting for technology, using conventional approaches. And three, look, decisions made earlier in the design process, demolish and rebuild versus adaptive reuse, for example, have a more significant influence on embodied carbon than the material changes. Thank you very much. I am now going to pass over to, oh, sorry, Alison, over to you.
Thanks so much, Phil. That was an excellent presentation. I just wanted to remind everyone, please keep those questions coming. We'll answer them at the end of Ross's presentation. I'll pass over to Ross.
Can you see that?
And
yep.
See if you can just click full screen. Should be good to go.
Can't see the bar is in the way. Oh, interesting. That's not a little problem here. Here we go.
Perfect. Thanks.
Terrific.
Ross.
Okay, well, I'm talking on some similar themes with Philip, and a tiny bit of overlap, perhaps hopefully reinforcing. So the theme for mine is inspired by Bill McKibben's statement that winning when it comes to climate change, winning slowly is the same as losing. And I probably get a bit serious about this stuff, and excuse me if I get overly heavily at times, but the real challenge for us is that we're not acting with the speed that we need to meet the timelines that are required to be avoiding the famous 2 degrees or 1.5 degrees. And this table, I guess, really makes the point. It's a NASA table of CO2 in the atmosphere from the last 16 years. And in the last 16 years, the CO2 in the atmosphere has increased 20%. So we're not pulling that down. And that was reinforced. So again, winning is the same as winning slowly is the same as losing when it comes to climate change. Our actions need to be much more focused, much more holistic. And that was reinforced by the UN's publication in October last year that our climate plans are insufficient and more ambitious action is needed, because on current commitments, we'll increase the emissions by 10% by 2030. Compared with 2010 levels. So just to reinforce, because I always feel the need to reinforce the sense of urgency, because this table that comes from the IPCC report from last year just shows the different options that come in terms of the potential trajectory of temperature increase. And hopefully the red one is we're never going to go anywhere near that, but we do still have the potential in the light of particularly what Philip just said about our report about we could actually reduce it by 50% today if we took the appropriate action. And I guess the things I'm talking about are trying to support that. Because if we get onto that kind of trajectory, there is a chance that we can actually start bending the temperature curve back down by the end of the century. So all these things are in our hands, and 80% of the problem is in the construction in cities. So our part of this turf, sorry, 40%. Did I say 80%? 40% of the carbon problem is in buildings and cities. So, and to reinforce and remind us again, the Earth is warming 170 times faster than in the last 7,000 years, and we've never had a temperature of 2 degrees above pre-industrial times in the last 3 million years. So these are quite unprecedented times. And the key thing about the 2 degrees is that it's potentially, according to these wonderful people at the Potsdam Institute, including Will Stefan, who's at ANU, is the 2 degrees is a potential tipping point where the Earth's systems shift from a self-cooling mechanism to a self-heating system. And that's what we obviously mean when we're talking about hothouse, that the Earth turns into a hothouse kind of environment it's warming itself up. It's no longer cooling itself down like it does now, and then things are really out of control. If you really want a dramatic detail, then if we lose the ice that we currently have on the Earth, the sea will rise 60 meters. So the whole of the coastal plain that I'm sitting on in Western Australia will be beneath water, and the waves will be lapping at the foothills of the Darling Scarp. So we obviously can't entertain that. But as you know, I think the spirit of Philip's contribution was that there's much in our hands to do about it. And the scale of what we can be working on is huge. There's estimates that in the next 30 years, there'll be 80% new build or rebuilt of what we currently have. And you can't manage what you can't measure, what you don't measure. And the focus is on whole of life carbon measurement. So I'm going to be quite focused on that. And changing the conversation for what appears to be feasible or practical, what people think they can achieve, to what's necessary, so that we don't stay on that pathway of winning slowly is losing. So I'm a great supporter of 50% reduction by 2030, various targets that are bandied around, but I think we should be thinking in terms of 50%, and that means whole of life carbon that's 50%. And to do that, we need a holistic change in the culture of practice within the profession now. I don't think we have a culture of practice in Australia that is thinking this way. We've got a lot of terrific work being done by a lot of terrific people, but holistically, this is not where the profession is at. And a key kicking point to get onto a pathway is to start measuring, so we can actually see the impact of our design decisions on carbon. And once you can see it, then it changes people's culture. So start reporting, build a knowledge within the profession, build consulting capacity to support that, because at the moment there's not enough consulting capacity to support the whole industry measurement. And we can also, in doing that, start building a database and not get worried about the variations in reporting numbers, but get into the practice of measurement and reporting. Start measuring whole of life carbon. So I was asked in this context to refer to a CPD series that I put together a couple of years ago called Zero Carbon Design, which is still sitting there. I think as of today, you probably can't access, but as of tomorrow, I believe we'll have fixed that. It's a series of 7 lectures designed to be an introduction. The first one is the fundamentals of energy demand optimization. I'll talk a little bit about that. Then there's one on energy supply side typology, depending on typology of building and geography. Life cycle assessment, a demonstration of eTool, which is one of a number of software platforms you can use. Then there's a computational modeling example by a couple of young guys, and shows how you can get real-time feedback in terms of your modeling of carbon. One on the circular economy and waste, one on living building challenge, and one on sort of structural options, which comes to the point that Philip was just talking about with the examples he just used. So the series is designed really on this cycle of maximize your passive design options for reducing energy demand on the building, reducing the use of fossil fuels and eliminating them, on-site renewables where possible, limiting upfront carbon, and so forth. That cycle of all of those actions that Philip talked about. So I just want to start with lecture 3 a bit on life cycle design. And again, picking up on Philip's point that it's about the construction phase, getting materials, transporting to manufacturing, transporting to site, the construction itself, use phase, maintenance and replacement and servicing of the building, and then end of life phase. And the platform that this is most commonly sitting on in terms of standards is a standard called EN 15978, which is very commonly used around the world, which picks up these phases. And the life cycle measurement process is structured around each of these stages. So the product stage, the construction stage, which is the upfront carbon, the in-use phase, and the end of life stage, which is whole of life carbon. And then there's the circular economy, with trying to maintain materials use within the industry and not going into a hole in the ground. I'll touch on that a bit. So Richard Haynes presented the demonstration of eTool, and I'll include this one table from his, which shows the kind of information you get out of something like eTool. I mean, there's lots of different ones available. He just happened to be available sort of next door to come in and talk. So, this shows that all of the different material elements have their carbon. This is a case study that he put into Revit, it's one of the great things. You can bring a Revit model, if it's a well-developed one, interfacing with the software, and it'll give you a readout of where the carbon sits in the materiality through the building, so you can see where to take action. And not surprising, the biggest numbers are in the base building, the structure and the substructure of the building, which is, always the case. And this I guess gives us a bit of a picture of the world that's coming. It's from LETI, London Energy Transition Initiative, a group of around 100 relatively young professionals that got together to build this material. And I'd recommend looking at LETI on site. You can download their reports and their databases. But this is creating a picture of across different use typologies, the different amount of carbon per square meter for each element, and driving it down to a pathway of zero. So we will eventually be sitting in a regulatory environment which will be limiting the amount of carbon per square meter across different uses, and we'll eventually be driving towards zero. So I think it's always helpful to see the picture that's coming, that there will be limits set on how much carbon you can be used in a building as we move forward. And again, with LETI, they in the English context suggest that 48% of the whole of life carbon, embodied carbon, is in the superstructure, 17% in the substructures, sort of aligns roughly with some of the numbers that Philip had before, 16% in the facade and 15% in the services, and 4% in internal finishes across those various phases of the carbon life cycle. That shows where the action needs to be. So this is a terrific piece of work that these two young guys, Daniel and Tristan, put together for the series. And there's a little animation that shows in a grasshopper model, looking at the structure of the building, looking at, it's a timber building already, but you can see with the bar chart of the red and the blue, it's already low on embodied carbon, but the red and the blue are giving us the picture of the embodied energy and embodied water. And you can see here they've gone to hollow sections of timber, box sections, and more than halved the amount of carbon. So you're already in a timber building, like moving to a box section and then iteratively fiddling with the structural form, you drive the carbon down. So it's a great way to do it in a grasshopper model. You're fiddling with the stuff in the grasshopper framework, and you're driving the carbon down while you're doing it. So there's lots of other people in the country doing good work. Fitzpatrick have built a platform around structure again. There's tools like Tally. Tally Cat is the latest iteration, built by Kieran Timberlake, great architects in America. But this is an open access integrated with the desktop, designer's desktop. So this is the world we're moving into, where these things you can work with on your desktop, and there are many architects who are building their own versions of these. So the basic back to basics. This one by Prasanna was the first lecture in the series, which talks about the fundamentals of managing the operational energy demand on the building, orientation, form factors, massing and shading, window performance, window and water ratio. You can see the great difference of the heating and cooling load on the building according to the orientation of the building. So that should impact on the design decision straight away. The form factor of is it a sort of efficient external envelope to fully enclosed floor area, can make a huge difference to both the cost but also the energy loading on the building. You can see here different form factors as you move through complex single story up to consolidated multi-story, and how the factors reduce. Glazing systems obviously a big factor. Here as table goes through a 19 apartment development they were working on, from single glaze low E on the left hand side to double glaze thermally broken on the right hand side, and you can see the thermal loading changes dramatically according to which one you use. Wall to window ratios in section J is obviously a big factor that's now in people's minds when they're designing. And you can see in this table how you can dramatically change the impacts of on your energy loading on the building with these formats. And it relates to section J, and this little diagram shows that if you want to concur with section J, how you have to dial up the glazing system if you want to increase the glazing amount in the building. If you use all of those tools are available to everybody in every design they do. And this little example he showed reduced the energy call on the building of 78% for operational energy. So that's going to remain, even though if we go to a green electricity grid, there's still a massive amount of resources that go into generating that electricity. So we shouldn't ever forget the need for optimization of energy demand on buildings. It's always going to be a big factor There's another lecture around living building challenge, which I think I won't try and go into today, but includes the red list, which I commend to everybody to be mindful of in terms of avoiding certain kinds of materials in buildings. And the circular economy, which is all where it's all going, a talk by Jenny Campbell referring to the great work by Ellen MacArthur Foundation on the circular economy and how to keep buildings in the life cycle, returning to phases in the manufacture for minimizing servicing requirements during the life of the building and so forth. And that's pushing a big factor in England now. There's a huge debate about demolish or not, and this is one of the high-profile projects, the Marks and Spencer's building on Oxford Street, that set the architects up against the protagonist Simon Sturgis, who is a great proponent of all that we're talking about. And that's brought to the forefront some of the issues around life cycle assessment, and we're still in the very early stages of a proven accuracy of the numbers, but that will evolve with sophistication and time and practice. And there are some great examples. This is the one that Philip just showed us of adaptive reuse of substantial parts of buildings being reused. There's a couple in Melbourne. Good examples again of where the existing building's being kept and they've built on top. This one by Fender Castellides in Collins Street. And ultimately, we would be aspiring to a regenerative situation where everything's returned to use. And Philip's point about building banks. This is a bank building, headquarters of Triodos in the Netherlands by Rauw Architects. The whole building has been designed to be dismantled. And interestingly, to your point, Philip, this is a bank and they have all of the materiality of this building on their balance sheet. So it's sitting on, they've actually logged the whole building components and it's on their balance sheet as assets for future use. It's not being written off in the normal way that balance sheets work. So it's a fascinating little example of the point you were making. And it doesn't necessarily look like a building that's immediately ready for demolition, but everything can be unscrewed and taken away and reused. And finally, just to build on the point that you were making, Philip, again, this is from Bureau Happold, a terrific group of architects, engineers based in the UK, but with offices all over the world, where they show how you can, whether it's concrete or steel or timber, there you can use strategies for reducing the carbon in all of them. So it's a very simple little structure. So it's in the concrete one, it's only 331 kilograms per square meter, and the timber one's only 142. But even within that simplicity, you can start a process of iteratively driving down. So on the left-hand side, if you can see it, you can see what happens if you take the 331 and you use blast furnace slag, then you get down to 175. Just using the column grid, which starts at a 9-meter column grid and getting down to a 7.5 or a 6-meter column grid, you can massively reduce the carbon, embodied carbon in the building. It goes to loads, how the foundations are designed, whether they're piled or whether they're slabbed, and how much concrete in the flat plate footings. But we might have to lose our love affair with the column-free grid in office buildings, because you can massively reduce the amount of carbon by allowing some internal columns in the floor plates of office buildings. So I'm sure that will become an ongoing debate. So just there's a range of different strategies here. So I commend this to you, to the the Bureau Happold website to dig this out. But it's a terrific little piece that shows how quite obvious available design decisions, working closely with a structural engineer, preferably as early as possible. Again, to Philip's point about that graph, that the big gains are made at the very beginning of the process. We must move to a culture where we're working with our mechanical and our structural engineers right from day one when we're considering the options for the building we're looking at. So it doesn't matter whether it's steel or whether it's timber, the options are still there. And here's an interesting example of what happens with steel when you reduce the column grid as well. The sections, the kilograms, the total weight of the steel dramatically plummets. And even with timber, this shows we start with 142 on the top left, and we end up through iterative operant to get down to 80. But even beyond that, Bureau Happold is showing that there's further iterations you can be getting down to. And one of the things I find really challenging that I would like to find more about, on the left-hand side there, they've got concrete down, using everything you can throw at it, getting it down to 54 from 300. So I think the conversation around concrete is still alive. I think we need more of this kind of thinking to be fully testing the veracity of using concrete, notwithstanding the fact that we're running out of sand. That might be the ultimate killer and limitation on concrete, not having sand. But I don't think that's a problem in Australia just yet, but it is a global problem of, the things that are being done to mine sand for concrete are appalling around the world. Loss of beaches and whole islands have disappeared and so forth. But in terms of the framework of our discussion today, I think there's the conversation around concrete, I think, should stay, very alive and well for a lot longer. We shouldn't be just simplistically dismissing it. And the digital age we live in, I think we're very lucky that we have these tools now available to us. We never had them before, and we've got a whole generation of young people coming out of university with skill sets that we're going to have to be listening to better than perhaps we have in the past, and fully integrating science into practice in a way that the profession hasn't been brilliant at in the last 100 years or so. And finally, to reiterate on the point, the grid becomes greener, and maybe a loss of sort of focus on the operational energy side of things because you're using green energy, but it still takes massive resources. I heard a talk recently where the chap was saying that the largest solar farms in the world, we're effectively going to have to build one of those every year for the next 30 years to generate the power that we will need in 2050 from renewables. So the resources that are going to go into that are very considerable. So don't lose the focus on low energy buildings. Thanks.
Thank you so much, Ross. I'd like to stop sharing your screen.
Yeah, I'm just trying to type it. The cursor that will allow me to do it.
I mean, I think there's some amazing content. I mean, those were two very, very comprehensive presentations. So thank you both. I think what really starts to highlight is the role that architects do play, and the ability that they have to really have significant influence on embodied carbon throughout the whole design. I mean, I think what I was really reflecting on, I guess, is that sort of net zero is sort of a pathway towards regenerative design and a circular economy, and that really is important to keep front in mind when thinking about designing to reduce carbon, because thinking of long-term adaptability of a building becomes then as equally important as thinking about that upfront carbon equation. So I might just sort of read out some questions from the group. I'll start with this one. Are hybrid materials structures as reusable as single material alternatives? I might pass that. Phil, or who wants to tackle that one?
I don't know. And part of the challenge is we don't, you go back, there's lots of buildings that have been built to be deconstructed and they very rarely get deconstructed. And this is a challenge we face, is the uncertainty of the future. We don't know what technologies, systems, societies will exist in 50 years' time. I think the Nagakin capsule tower, that was due to all be prefabricated and pulled apart, and is currently being demolished, and the pods are going to be put in museums around the world. So, and then I think of a great building like the Macquarie Incubator, which was designed to be deconstructed, but it's such a great building that might never be deconstructed. So it's difficult to tell. There's some trends, in guidance, which is never glue anything together. Make sure the layers of the building, the structure, the systems, the finishes are separate and can be pulled apart. I think there's some general principles to follow there, but I'm not sure about the difference between hybrid and single kind of material.
Did you want to add into that? I mean, I think from my perspective, it's all about sort of avoiding contamination. So I think that was probably a fairly strong thing, I guess, to think about supply chain, and thinking and looking back at some of those previous examples that you showed, Phil, around, we have these amazing warehouse buildings that we're still using, and even, starting to think about how do we actually disassemble them carefully and reuse them in design. So I think there's many, as you say, there's a lot of technological change, rapid change. But I think, even just thinking of having that almost materials passport for every building is a good start.
And it's a lot of it's about conversations as well. As a profession, we can work closer with demolition contractors to see, you know, and every case study where they have shown high levels of reusability, it's not been a technological thing, it's been an organizational logistical thing. It's been about building relationships with different contractors, with different people down the supply line earlier or in a different way. So I don't think there's, you know, we're not going to invent some incredible technological solution to this. It's going to be logistical and relationship wise.
Yeah.
I think one thing I would add is if we focus from the beginning on standardized dimensions of product and materials like sheet sizes and stuff like that, then that will make it easier for deconstruction, because it's more likely that consistency will translate into other contexts. You know, dimensions of, if the question was about the beam that Philip showed, then I guess one of the fundamentals is, you know, how is it fixed, and you know, what's its dimension, and how likely is that dimension to be appealing in the future. But you know, it's still a heck of a lot easier to demolish and reuse than an in situ poured concrete structure is.
Yeah, and I think one additional point to that is thinking about use, longer term use. So actually, you know, extending that into, you know, having higher ceilings potentially for, you know, allowing different types of uses to come in, and just thinking about the design in that sort of adaptive long-term mindset, thinking of certain aspects of the design, sort of the long life, loose fit, long life kind of principles.
Yep.
Yeah. I might move on to another question here. I think this one is going to be right in your alley, Ross. So you sort of touched on this, but I think maybe you could elaborate. So there are a zillion carbon calculators and databases. What are the best ways for the profession to collectively use evidence-based design decision-making tools consistently? Should it be a goal for there to be a single source of truth on carbon calculations?
Single source is, I think, a worrying concept, and there is, and Philip knows this very well. You know, the current debate around the world is very live around the veracity of the data coming out of the tools, because it relies on databases for materials. So you've got environmental product declaration statements, you've got databases like EPIC and ICE and others. I mean, there's, you know, I think when we get to the point where there is universality of EPDs on materials, then the consistency of reporting is going to be stronger. But the reality is that we're in the very early stages of development of a relatively sophisticated science in calculating the carbon in the building. But that shouldn't stop us starting to the point about winning slowly is actually losing, because we need to get practiced in this stuff. It's not part of our current kit of parts generally across the industry. And you know, both I and Philip focused on, you know, iterative changes to design to drive carbon down. And in the end of the day, if you've saved 50% of 100 compared with 50% of 120, does it really matter? The point is you've saved 50%. So the tools give us the opportunity for taking action, seeing the result of our actions as the numbers come down, hopefully not up, and that becoming a norm in our practice, because it builds knowledge within the profession and individual practices about the impacts of these iterative decision making. And then it becomes the norm of practice. And that's what I mean about the changing of the culture of practice, that decisions are being fueled and filtered by the impacts that they have on carbon, and you can see it. You know, there's a lot of hope being placed around the Neighbours platform that's being built at the moment. The one thing, which I think is a terrific initiative, the one thing I'd worry about is everybody stops and waits until there is an agreed, universally, you know, accepted norm. Then we're worse than winning slowly. We're actually literally going backwards. And I think UK is much more advanced in this than we are, and I think we should learn more from what's been done in the UK over the last 10 or 15 years than we are. And there is a lot more acceptance of a framework for it, notwithstanding examples like the Marks and Spencer case, where they're all fighting because the developer wants one outcome and the city wants another. But the City of London is just about now, so it's introducing a requirement for whole of life carbon reporting on all of its buildings, which I think is a terrific step forward in this. So half an answer to a question, because ultimately I think we won't have a universal framework for. We will eventually have a regulatory framework in Australia, as I was alluding with the Letty references. But for the moment, we need to lead by measuring ourselves.
Yeah.
I mean, I'd just say we can't let the perfect be the enemy of the good.
Yeah.
Got to start somewhere. I mean, it's like measuring operational energy back in the 70s. You know, that's kind of where we are. But we've got to start measuring. We've just got to start measuring. And I'm less concerned if there's some inconsistencies in there, because, you know, there's more calculators than I've had cups of tea out there at the moment, I'm afraid, which for some people is bewildering, and it's understandable. I think we train all our students firstly in Excel. We get them using the very basic. Then we use Tally with all our students as well. So all our students do life cycle carbon on their studio projects and the masters, all using Tally. But I'm not necessarily saying that's the best way of doing it. It's just about getting into the routine of measuring, design, measure, and analyze, redesign. That's what we talk about to our students, you know, and whether that's consistent with someone else measuring doesn't worry me as much.
And I think one of the things that it's interesting. I mean, I have to say this. So Philip's table that showed the targets from different countries and different organizations and institutes didn't include anything from Australia. So I think, you know, that's a signal for where we're at and where we need, you know, we do need to become committed to targets.
I included the GBCA.
Well, okay, sorry, you did too. Yes, that's a good one. That's a good one. I take that back. I was probably referring to another one that wasn't there, but you know, I think as a profession, we need to have a position, and we need to understand why we have a position.
Yeah, absolutely, absolutely. On this, I mean, this is a kind of a pertinent question. You know, can practice do this alone? We are the agents for change and must promote, convince others who finance, build, and use projects. So does ultimately the hammer of legislation have to land on the industry overall to ensure that all buildings, not just architect design, does include the required reductions?
Yes, we should be leading. The regulatory hammer, if that was the word that was used, will ultimately come because it has to, because the whole industry has to be regulated to make sure that, you know, as a country, we're achieving the goals that we're committed to with our international commitments, apart from anything else. But I think where we're at the moment is that industry should be leading the pathway towards that regulatory environment and becoming greater contributors to the formulation of that regulatory environment. And that's something that we're not particularly serious participants in either. We're kind of leaving it to others too much.
Yeah. And I would say we're seeing industry shift pretty quickly in terms of financing of projects, other sort of ESG kind of commitments across client groups, bodies. So there is a real shift, I think, rapidly happening there.
And we need to have a voice in the room, and we need to become conversant with the language and the technology and the technical side of this, so that we're in the room, you know, driving outcomes, not waiting to be told what to do, because so much relies on the creativity of the designer in these outcomes. Yeah. So Philip, you probably have something to say on that as well.
No, I was just going to look, it's slow moving. We know neighbours are going to have a rating system for embodied carbon in the next 2 years. As of October this year, basics will require embodied carbon measurement. Both of those are just about measuring. They're not about setting a cap. The next stage after that will be a regulatory cap, i.e. you cannot exceed or do not exceed 800 kilograms per square meter or whatever. And then there'll be hopefully ratcheting down on that cap. What we can see in other places, in France, they've got that. Now you cannot build above 660 kilograms of CO2 per square meter. Denmark have got a cap. The Netherlands have got a cap on whole life cycle. So we're starting to see that happen in the regulatory space. I think that's great. What I'd like to see is a bit of stick and carrot, where, okay, we start to regulate, but also we say, well, look, if you can reduce embodied carbon by 50%, there's a 20% FAR bonus or something like that. That will really start driving innovation. And we know we exist in a risk-adverse industry. The second you've got a bit of carrot and the second people start really doing it, that will drive change.
And interestingly, there's one local government in Australia that requires whole of life carbon reporting at its development approval application stage. It's the city of Vincent in Western Australia, funnily enough. They did that about 7 or 8 years ago. In about 2 or 3 years, they introduced a requirement to not only report, but demonstrate that report is showing 50% improvement on 2010 figures. So why they're way ahead of the rest of the country is a surprising thing. But what they also give feedback is that since they introduced the benchmark, because they'd already had 5 or 6 years of requiring reporting, the designers knocked it out of the park. The 50% hurdle wasn't at all difficult to achieve. And it comes back to your point in the ARIT report, Philip, that it's all there available to us now to be doing it. You know, there's one case study that shows that in terms of the government regulatory environment.
Thank you. I mean, I think now we've reached the end of our session. Apologies to, thank you for all the questions. Apologies to those who we didn't quite get to. But I think this session is going to is recorded, so it'll be shared, I think, in the coming weeks. So please keep an eye out on the links, and you'll be able to have access to the information presented today. So I just wanted to, thank you, Phil, and thank you to Ross for your amazing presentations. And I really hope to see some action in this space and, much more conversation. And I think, to Philip, it's about relationships, it's about collaboration to really move this forward. So, just thank you for your time. And I hope everyone has a wonderful afternoon.
And I'll ensure that those lectures are back online. I think they're offline at the moment, but I'll fix that up if anybody wants to have a look at them. And Phil's report, your paper will be coming out soon, Phil. Your Acumen.
The Acumen's currently under peer review, but hopefully it'll be out soon, yeah.
Terrific.
Great. Thanks so much, everyone.
Bye.
Bye.